The autumn of 1943 found First Lieutenant Kenneth Walsh on Bougainville in the Solomon Islands, hunched over his logbook with pencil in hand. What he recorded that September day would mark a turning point in how air combat evolved across the Pacific Theater. The new fighter aircraft represented a leap forward. Speed and firepower now gave American pilots capabilities their Japanese opponents simply could not counter. But there remained a critical problem. Accuracy in the air remained elusive, especially when both planes twisted and turned through violent maneuvers. Walsh had just returned from escorting Navy bombers, his F-4U Corsair's scratched canopy still catching the tropical sun. He'd watched experienced pilots struggle with something that seemed impossible, striking a target that refused to hold still. Both aircraft spinning, climbing, diving, executing evasive patterns at tremendous speeds. The mental mathematics required to compute where an enemy plane would be when your bullets finally arrived seemed beyond what a human mind could calculate in mere fractions of a second. What Walsh and thousands of other Marine and Navy pilots didn't realize was that the answer already existed. British engineers had cracked the problem years earlier. Within the coming year, a remarkable device incorporating spinning gyroscopes and precision optics would reach Pacific squadrons. This Mark 18 gun sight would transform aerial gunnery from a mysterious art, mastered only by the naturally gifted, into a skill that nearly anyone could learn in weeks. The Corsair itself had entered service just months earlier, in February 1943, and it possessed capabilities that had never before been seen in American naval aviation. The Pratt & Whitney engine pumped out over 2,000 horsepower, driving the aircraft past 400 miles per hour, the first single-engine American fighter to achieve that speed. 6 Browning machine guns, each chambered in .50 caliber, could unleash devastating streams of fire, with each gun capable of rattling off nearly 800 rounds per minute. When those bullets connected, the results were catastrophic. The problem was making them connect. Deflection shooting, the art of hitting a moving target while flying at high speed from a moving platform, represented aerial combat's greatest challenge. Picture the scenario: a Corsair screaming through the sky at 400 miles per hour, attempting to rake a Japanese Zero maneuvering at 300 miles per hour. The pilot couldn't aim at where the enemy was at that moment. Instead, he had to aim at a point in empty sky ahead of his target, calculating where the Zero would be when the bullets arrived. Those bullets left the gun muzzles at roughly 2,700 feet per second, yet they still needed time to traverse the distance. At 500 yards, that interval stretched to approximately half a second. In that half second, a Zero executing a standard rate turn would drift nearly 200 feet across the sky. The pilot had to lead by exactly that amount, continuously adjusting as ranges shifted and angles changed. Meanwhile, the G-forces built up, narrowing vision to tunnel-like focus and making complex mathematics feel impossible. The Mark 8 reflector sight mounted on Corsairs through 1943 and into 1944 offered little help. It projected a simple illuminated reticle, nothing more than a fixed circle showing where the guns were pointing. Everything beyond that was the pilot's responsibility. Experience and intuition were his only tools. Pilots with natural talent spent months developing a feel for deflection shooting, learning to sense the correct lead angle almost instinctively. Many pilots never developed that feel at all, forever spraying ammunition across the sky behind fleeing targets, watching bullet trails that never found their mark. First Lieutenant Kenneth Walsh represented the exceptional category. Flying with VMF 124, he'd mastered deflection shooting through countless hours of practice, combined with a rare natural gift for three-dimensional motion. On May 13, 1943, he'd become the first Corsair ace, downing 3 Japanese fighters in a single day to reach 6 confirmed victories. Walsh understood the geometry without thinking about it, the way a master musician understands a piece without reading the notes. The average Marine pilot arrived in the combat zone with perhaps 200 hours of total flying time behind him, maybe 20 hours of actual gunnery practice against slow-towed targets flying straight and level. When such pilots encountered experienced Japanese pilots in agile Zeros, the result was often frustration and failure. Combat reports throughout 1943 told a grim story. Pilots would expend their entire ammunition load without scoring a single hit, their bullets passing harmlessly through empty space, arriving too late because the mental calculations lagged by critical fractions of a second. The British had identified this problem early in the war. By 1941, they were producing the Mark II gyroscopic sight, a device that seemed almost like science fiction. Inside its housing, spinning gyroscopes resisted any change in orientation. When an aircraft banked or turned, those gyroscopes maintained their pointing direction while the plane rotated around them. Precision gears and mirrors measured this resistance, calculating the aircraft's exact rate of turn. That rate corresponded directly to the lead angle required for a hit. The sight automatically adjusted the aiming reticle, moving it ahead of the target by precisely the correct amount. Spitfire pilots reported extraordinary results. Pilots who had struggled for years with deflection shooting suddenly found their bullets connecting on the first burst. The sight eliminated mental calculation entirely, freeing pilots to concentrate on tactics and positioning. American military leaders recognized the potential immediately. They contracted the Sperry Gyroscope Company to manufacture American versions. The Army Air Force called theirs the K-14. The Navy and Marine Corps designated theirs the Mark 18. Both were fundamentally identical to the British original, with only minor modifications for American production and cockpit installation. At peak production, Sperry's facility in Lake Success, New York employed over 20,000 workers, turning out these gun sights alongside bomb sights, fire control systems, and navigational equipment. The Mark 18 was substantially more complex than the simple reflector sight it replaced. Where the old sight weighed perhaps 5 pounds, the new gyroscopic system weighed 12 pounds and required significant cockpit modifications. The engineers explained that this bulk was essential. Inside the housing sat 2 independent gyroscopes, spinning continuously once powered, constantly measuring pitch and yaw. These tiny spinning instruments held the secret to solving the deflection shooting problem that had confounded fighter pilots since the First World War. The Mark 18 displayed 2 separate reticles to the pilot. On the left, a fixed cross showed where the aircraft's guns were actually aimed. On the right, a gyro-stabilized reticle appeared as a center circle, surrounded by 6 diamond-shaped pips. This moving reticle showed the computed aiming point. As the pilot maneuvered to track a target, the gyroscopic reticle positioned itself automatically ahead of the enemy aircraft, always placing the lead angle at exactly the right distance. The pilot's procedure had become remarkably simple compared to the old reflector sight. First, he selected the target's wingspan using a control on the sight itself, choosing from known measurements of Japanese aircraft. The A6M0, the most common opponent in the Pacific Theater, had a 36-foot wingspan on standard variants. With this selection made, the pilot twisted a grip integrated into the throttle lever, expanding or contracting the diamond-shaped ranging reticle until it matched the apparent wingspan of the target as viewed through the sight. This mechanical action set the range, telling the sight's ballistic computer the precise distance to the target and how much bullet drop compensation would be necessary. Range and wingspan established, the gyroscopes assumed command. As the pilot maneuvered to track the target, the moving reticle automatically positioned itself ahead of the enemy aircraft by exactly the correct lead angle for the current rate of turn. The pilot simply placed that computed reticle on the target and pressed the trigger. The bullets would arrive precisely where the sight predicted, regardless of how violently both aircraft were maneuvering. Production began in earnest during spring 1944. The Army Air Force received priority for European operations, with P-51 Mustangs and P-47 Thunderbolts receiving K-14 installations beginning in August 1944. Navy and Marine forces followed closely behind, with Corsairs and F-6F Hellcats scheduled for Mark 18 retrofits through the fall and winter months. The first Corsair squadrons equipped with the Mark 18 were those preparing for carrier operations, VMF 124 and VMF 213. These squadrons trained at Naval Air Station Santa Barbara in late 1944, receiving their gyroscopic sights during this period before joining the fleet in December and bringing the Corsair into carrier-based combat for the first time. Lieutenant Robert McClurg, flying with the reformed VMF 214, received his Mark 18 equipped Corsair in early 1945. He'd scored several victories during 1944 using the standard reflector sight, but when he first handled the new system, he grasped its revolutionary potential immediately. In a letter preserved in Marine Corps archives, McClurg wrote that the Mark 18 represented the difference between educated guessing and mechanical certainty. Years of accumulated experience were now compressed into just a few hours of training. Japanese naval aviation intelligence learned of American gyroscopic technology in late 1944 through analysis of recovered Corsair wreckage and captured technical documents. What they discovered deeply troubled their commanders. The specifications confirmed that Americans had developed a fire control system that essentially eliminated human error from deflection shooting. Japanese tacticians understood a bitter truth immediately. No amount of improved training or tactical innovation could overcome this advantage. Gyroscopes, spinning thousands of times per minute, operated with mathematical precision that no human reflexes could match, regardless of a pilot's experience level. Japanese fighters had survived thus far by exploiting their superior maneuverability, forcing American pilots into difficult deflection shots where human calculation errors provided a margin of safety. Mark 18 equipped Corsairs changed that equation entirely. Any American pilot capable of tracking a Japanese fighter long enough to set range would score a hit, no matter how complex the maneuvering became. Tactical orders went out across all Japanese naval aviation units. Fighters were instructed to avoid prolonged turning engagements with Corsairs at all costs. The new doctrine emphasized hit-and-run attacks, diving from altitude, making a single firing pass, then extending away at maximum speed. This shift acknowledged an uncomfortable reality. Japanese pilots could no longer depend on maneuverability alone to survive against this new technology. December 1944 marked a milestone for Corsair operations. VMF 124, under the command of Major William Geezer, became the first Marine fighter squadron to operate from a fleet carrier when they joined USS Essex at Ulithi. VMF 213 arrived simultaneously, bringing 48 F-4U Corsairs to carrier operations. Both squadrons were equipped with Mark 18 gyroscopic gun sights, representing the leading edge of American aviation technology. The Essex Air Group departed in January 1945 for strikes against Formosa and the Philippines. Marine Corsair pilots flew combat air patrol, escorted bombers, and participated in strike missions, finally bringing the F-4U into the carrier-based role it had originally been designed for. The Mark 18 proved invaluable during these operations. Pilots engaging Japanese interceptors reported significantly improved hit rates compared to their previous experiences with reflector sights. Combat action reports from January and February 1945 documented numerous instances where pilots achieved kills with their opening burst, a level of first-pass success that would have been rare with earlier systems. When bomber escort missions flew, the difference became starkly obvious. Corsairs had to hold their formation positions steady, which often meant they couldn't get into the angles they really wanted for an attack. But here's where things changed. The Mark 18 gave pilots something pilots never had before. It could figure out accurate deflection shots from practically any angle. Suddenly, those tight formations weren't a prison anymore. Pilots didn't have to fight their way into that perfect spot directly behind an enemy aircraft, the classic 6 o'clock position that had always been the target. They could open fire from angles that would have been completely useless with an old reflector sight. When February 1945 arrived, so did the invasion of Iwo Jima. Marine Corsairs became the shield overhead, providing constant air protection for the assault force pushing ashore. Multiple squadrons launched from escort carriers, circling above the invasion fleet in combat air patrols and helping support the troops below. During these defensive missions against Japanese air attacks, the Mark 18 showed what it could really do. Pilots intercepting incoming raids were getting kills at ranges and from angles that would have seemed impossible with the older sighting systems. The gyroscopic sight's automatic deflection calculation was doing the hard math instantly, letting pilots fire at multiple targets one after another without wasting precious ammunition. A pilot with just a reflector sight might burn through all his bullets trying to bring down a single difficult target. But a pilot with the Mark 18 could put rounds on 2 or 3 different aircraft during the same fight, making every shot count and turning limited ammunition into multiplied fighting power. The squadron commanders reported something striking in their official summaries. Less experienced pilots were matching the combat success of the veterans now. The improved fire control was leveling the playing field, giving younger, less seasoned pilots the kind of accuracy that used to take years of experience to develop. As 1945 pressed on, carrier operations against Japanese territory intensified. VMF-214, flying from USS Franklin, joined strikes against enemy air bases and military facilities. Then on March 19, 1945, a Japanese bomber found its target. Franklin took a direct hit while operating off the coast, and what followed was catastrophic. The explosions that tore through the ship and the fires that consumed it killed over 700 sailors and aviators aboard, including 32 men from VMF-214. The squadron's losses were staggering, devastating in their finality, yet the survivors pressed on, continuing their missions after the Franklin managed to limp towards safety. That disaster exposed both the lethal reality of carrier aviation and the extraordinary courage it demanded from every pilot who strapped into a cockpit. But despite the bloodshed, Marine air squadrons kept flying. They kept providing air cover and striking capability for the fleet, refusing to yield. Then April 1945 brought Operation Iceberg, the invasion of Okinawa. What followed would be the most brutal, most relentless kamikaze assault of the entire war. Japanese forces threw thousands of aircraft at the American fleet in wild, desperate efforts to stop the invasion from succeeding. Marine Corps aircraft equipped with Mark 18 sights became crucial in the defense against these attacks. The gyroscopic sight had a particular advantage against kamikaze aircraft, whose attack patterns were predictable and steady. Range estimation and deflection calculation became almost straightforward. Pilots could see the incoming kamikaze, use the sight's ranging reticle to set distance, and hit them with that first burst with a consistency that would have been pure fantasy with reflector sights. From April through June 1945, combat air patrols resulted in hundreds upon hundreds of Japanese aircraft destroyed. The exact numbers, precise statistics that specifically credited kills to Mark 18 equipped aircraft versus reflector-equipped ones remain unavailable in the records that have been declassified. But operational reports from that period consistently emphasized one thing: squadrons that had received the gyroscopic sights were noticeably more effective in combat. The psychological toll on Japanese pilots who survived encounters with Mark 18 equipped Corsairs went beyond tactical defeat. It was something darker. Being hit regardless of how hard you maneuvered, watching tracers curve through the air with uncanny accuracy, watching the impossible happen repeatedly, it created a sensation of technological helplessness that no training could have prepared them for. After the war ended, Japanese aviators who lived through those battles described the experience in interviews. Many identified American fire control systems as among the most demoralizing weapons they'd ever faced. Once an American pilot got that tracking solution locked in, there was no escape. Maneuverability couldn't save you anymore. Experience didn't matter. The only option was to avoid the fight entirely, and that was tactically impossible when you were trying to protect your own ships and ground forces. The Mark 18's inner workings represented something remarkable: a machine that could do mathematics without electricity. It used nothing but mechanical linkages, gears, and mirrors to solve problems that would puzzle a trained mathematician. Gyroscopes spun continuously once the sight powered up, keeping their orientation stable through the physics of angular momentum conservation. As the aircraft twisted and turned through the sky, the gyroscope housings rotated around those stable spinning rotors. Precision gears inside measured this relative motion, translated it into mirror movements that shifted the aiming reticle into the correct position. The entire mechanism operated with tolerances measured in thousandths of an inch, built using the most advanced machining techniques the country possessed in 1944. Sperry's production facilities represented American precision manufacturing at its absolute peak. Making each Mark 18 required dozens of individual components, each one machined to exacting specifications. The gyroscopes themselves were miniature marvels, with spinning bearings that had to rotate smoothly even under the intense G-forces of combat maneuvers, never binding or failing. Before any sight left the factory, quality control put it through rigorous testing. Test stands simulated aircraft maneuvers, checking that the sight computed deflection angles correctly across different turn rates and target distances. If a sight didn't pass, technicians sent it back for adjustment or complete rebuilding. The real challenge wasn't just making these sights, it was making them in the vast quantities needed to equip thousands of aircraft scattered across multiple war theaters. Sperry kept ramping up production through 1944, teaching workers the specialized techniques required for precision optical and mechanical assembly. The Mark 18 combined cutting-edge gyroscopic technology with American mass production methods, never compromising on quality. The design allowed for interchangeable parts, so different facilities could manufacture components separately and assemble them together. This modularity made maintenance easier too. If a site failed during combat, technicians could swap out individual parts instead of replacing the whole unit. Sperry parts were stocked at maintenance bases across the Pacific, keeping aircraft downtime to a minimum when a site needed replacement. Installing the Mark 18 into a Corsair cockpit required real thought about how pilots would use it. Engineers positioned it where a pilot could see it easily without losing situational awareness. The throttle-mounted range adjustment had to be within reach without forcing the pilot's hand off the flight controls. They worked closely with experienced combat pilots, listening to feedback about what made sense and what created problems during the intense pressure of actual fighting. The result was intuitive to operate, something pilots could use without having to divert their attention from the tactical situation unfolding around them. Pilots needed training to unlock the Mark 18's potential. The programs taught pilots what the sight was displaying and how to read its indications. They learned when the sight had settled after violent maneuvers, when they could trust the reticle's calculations, how to quickly set range using the diamond-shaped ranging pattern. Ground school covered the basic principles of gyroscopic deflection computation without drowning pilots in mathematical theory. The focus was practical skill, not engineering knowledge. Pilots needed to know how to operate it, not design it. Flight training included intercept practice against target aircraft, giving pilots real experience with how the sight behaved during tracking. Instructors emphasized smooth, steady tracking because jerky maneuvering could make the gyroscopes temporarily lose accuracy. The Mark 18 worked best when a pilot maintained consistent pursuit, letting the gyroscopes measure steady turn rates. Training also covered what the sight couldn't do. The gyroscopes needed several seconds to stabilize after violent maneuvers. A sudden reversal would cause the reticle to lag momentarily before reacquiring accurate deflection data. Experienced pilots learned to work within these limitations, timing their attacks to coincide with moments when the sight had achieved stable operation. Despite minor constraints, the Mark 18 represented a massive leap forward in fire control technology. Pilots who had struggled with deflection shooting using reflector sights now found themselves hitting targets with regularity that seemed impossible before. The sight didn't make aerial combat easy. It still demanded tactical judgment, situational awareness, and skilled flying. Combat remained dangerous and demanding, but the one thing that had always been hardest, actually getting bullets on target, had become predictable, reliable, and deadly. Measuring the Mark 18's total impact on Corsair operations in 1945 is difficult without access to all the records. Official statistics show that F-4U Corsairs achieved an overall kill ratio of 11-1 during the entire war, with 2,140 air combat victories against 189 losses to enemy aircraft, accumulated across more than 64,000 operational sorties. These numbers combined results from aircraft carrying both reflector and gyroscopic sights across the full span of the conflict. Separating exactly how much credit belonged to the Mark 18 would require detailed combat reports that remain classified or lost. What does exist is consistent testimony from pilots who flew both sight types. They uniformly stated that the Mark 18 made deflection shooting more reliable and less dependent on raw natural talent. Anecdotal evidence from squadron records, pilot memoirs, and operational summaries shows the gyroscopic sight delivered genuine practical advantages in actual combat. The Mark 18 program showcased American technological capability and industrial production at their height. It combined advanced gyroscopic technology, precision optics, and mechanical computing, all engineered to survive the hostile environment of combat aviation. It was produced in sufficient numbers to outfit thousands of aircraft distributed across a worldwide supply chain and serviced in forward areas by technicians working in primitive conditions. Success came not from any single brilliant breakthrough, but from every component of the system functioning effectively. British scientists had identified the core principle. American engineers adapted the design for mass production. American factories manufactured them in volume, and American logistics networks delivered them to where they were needed. The Mark 18 embodied the systematic approach to military technology that drove American war production. As decades passed after the war, Japanese aviation veterans published accounts and participated in historical discussions, and their perspective on the Mark 18 and similar Allied fire control systems gradually became clear. They reached a universal conclusion. American fire control technology had made Japanese tactical doctrine increasingly obsolete by late 1944 and early 1945. The maneuverable fighter piloted by a well-trained aviator couldn't match aircraft equipped with systems that automatically calculated deflection. Japanese post-war Air Force development reflected what they'd learned through hard experience. The Japan Self-Defense Force, established in the 1950s, emphasized advanced avionics and weapon systems over sheer aircraft agility. The pilots who had faced Mark 18 equipped Corsairs understood that future air combat would be decided mainly by technology rather than individual skill alone. The Corsair itself outlived the war by years. Marine squadrons flew F-4U aircraft during the Korean War from 1950 to 1953, providing close air support for ground troops and flying interdiction missions. Many of these planes still carried their Mark 18 gyroscopic sights throughout their service life. Technology that had seemed miraculous in 1944 had become standard by 1950, expected and unremarkable. This was the pattern of the post-war era. Capabilities impossible in 1940 were routine by 1950 and outdated by 1960. The shift of aerial gunnery from an art practiced by gifted individuals to a predictable science, accelerated by the Mark 18's arrival, moved toward its inevitable conclusion with guided missiles that eliminated the need for any pilot aiming at all. Air-to-air missiles, first used in actual combat in the 1950s, erased even the requirement that a pilot maneuver his aircraft to aim his weapons. The human hand became unnecessary to the act of killing. The transformation from basic reflector equipment to spinning rotor targeting systems to radar-guided missiles unfolded with stunning speed. Less than 15 years from start to finish. This pace of advancement had never been seen before in military flight history. When American aviators conducted operations over Vietnam during the 1960s, the mechanical principles embedded in the Mark 18 had evolved into vastly more complex fire control computers. These integrated systems combined radar distance measurement, automatic prediction of where to aim, trajectory mathematics, and target recognition into seamless packages that bore almost no resemblance to the mechanical calculator from 1944. Yet something fundamental hadn't changed at all. The core idea remained the same. Use spinning rotors to sense how your aircraft was moving, figure out where to point your guns, then show the pilot the answer in a way they could use it instantly. Statistics from World War II aerial campaigns reveal just how important the Mark 18 turned out to be. From 1943 through 1945, Navy and Marine pilots flew thousands upon thousands of combat sorties against Japanese targets. They achieved an 11-to-1 kill advantage that made their fighters among the war's most lethal aircraft. Several things working together created this remarkable success. The aircraft possessed speed that gave pilots choices. They could pick when to engage and when to break away. The sturdy frame meant it could take punishment that would have snapped lighter enemy planes in half. The formidable weapons package delivered devastating firepower when bullets found their mark. The Mark 18 sight enhanced these strengths by helping pilots place their shots with better precision. It didn't create the aircraft's dominance, but it amplified capability that already existed. Yet the pilot remained absolutely crucial. The sight helped them shoot straighter, but it couldn't teach them how to fight, how to read the situation, or how to make split-second decisions. Those skills demanded hard-won experience. What the sight did accomplish was shortening the training timeline for one particular skill, hitting moving targets during combat, something pilots once needed months of practice to master. Looking at the bigger picture, the Mark 18 was just one piece among many American technological advantages in the Pacific conflict. Warning radar systems spotted incoming aircraft and guided intercepts. Communication networks made coordinated strikes possible. Proximity-triggered anti-aircraft shells created invisible walls around vessels. Each innovation offered its own benefits. Combined together, they formed something Japanese forces simply couldn't counter. The Mark 18 followed this same pattern. It wasn't a single device that won the air war by itself. Rather, it was a sensible improvement in aiming systems that made already capable fighters even more effective. The contribution was steady progress rather than breakthrough innovation, yet that steady progress across thousands of aircraft and tens of thousands of individual combat missions produced powerful cumulative results. What the Mark 18 left behind extended further than just direct combat applications. Creating the sight demanded something unprecedented: genuine teamwork between physicists, manufacturing specialists, and actual combat pilots. University researchers contributed knowledge about spinning rotor mechanics. Factory technicians worked out how to produce them at scale, and fighter pilots offered hands-on suggestions for refinements. This partnership model influenced how weapons would be built going forward. The acquisition strategy also broke new ground. Rather than starting from zero, American decision-makers recognized a British innovation and figured out how to manufacture it domestically. This practical willingness to adopt external technology when it offered value showed the clear thinking that would serve American military aviation throughout the following decades. Methods created for producing the Mark 18 left their mark well beyond that specific device. The manufacturing approach used separate workshop facilities producing interchangeable segments, which made it possible to build in enormous quantities. This became the American advantage, the industrial foundation capable of making intricate precision devices at volumes other nations couldn't approach. These same methods later got applied to radar equipment, fighter engines, and electronics, creating a manufacturing network without peer. The aviators equipped with Mark 18 sights represented a bridge between two eras: pilots who transitioned from pure instinct-based gunnery to more methodical technology-supported engagement. Many chose to stay in uniform, flying jet aircraft, and later working in planning roles where they influenced how the military would fight using these advanced fire control systems. Kenneth Walsh, the first pilot to achieve ace status with a Corsair in 1943, had depended on nothing but a reflector sight and natural talent to shoot down enemy planes. He finished 1945 with 21 confirmed victories. For his bravery on August 15, 1943, when he charged into a larger Japanese formation despite his own aircraft being damaged, he earned the Medal of Honor. Walsh continued serving in the Marine Corps after the war, rising to the rank of lieutenant colonel before hanging up his flight suit. His lifetime in uniform spanned the journey from instinctive dogfighting to technology-enhanced shooting, from machine gun-equipped fighters to aircraft carrying missiles. Walsh embodied the larger shift in how aerial warfare evolved through the 20th century. Robert McClurg, flying with the reformed Marine Squadron VMF 214 in 1945, made it through the war with 7 confirmed kills. He remained in the Corps until 1965, retiring at the rank of colonel. Following retirement, McClurg documented the mechanical changes he'd observed throughout his flying years. He stressed that although the Mark 18 made deflection shooting more certain, nothing made combat safe or simple. The sight solved one piece of the puzzle, but plenty remained unsolved. Managing altitude, controlling your energy, staying aware of your surroundings, keeping tactical advantage. A pilot with perfect equipment could still get outmaneuvered, outclimbed, or simply ambushed by an opponent he never detected. Technology made fighting more effective, but offered no guarantee of walking away alive. The Mark 18's progression didn't end dramatically, but rather transitioned gradually into more advanced equipment. When jet-powered fighters replaced propeller-driven machines during the 1950s, newer fire control systems replaced mechanical rotor sights. The Mark 18 didn't abruptly stop working or lose all usefulness. It simply became obsolete because faster aircraft demanding engagement at greater distances required superior systems. Some Mark 18 equipment stayed operational aboard aircraft, providing ground support missions during the Korean conflict. Some went into warehouses or were dismantled as older planes left service. A handful made their way to museum collections, where they sit today as physical reminders of when machines performing calculations meant cutting-edge warfare. What the Mark 18 actually left behind doesn't exist in physical form anymore. Those artifacts belong in display cases now. The genuine inheritance lives in the concepts those machines demonstrated and the technological path they created. Every modern fire control system, no matter how advanced, traces its family tree back to devices like the Mark 18 that first tackled the fundamental challenge of automated aiming. Engineers who developed the Mark 18 contributed understanding that reaches well beyond their immediate accomplishments. They established that mechanical devices could perform intricate mathematical operations with sufficient precision for wartime application. They showed that operators could use sophisticated machinery when under extreme pressure. They demonstrated that complex devices could be built at massive volume and maintained far from factories. The pilots flying with Mark 18 systems added their own chapters to this history. They tested capabilities in actual combat and offered observations that improved how the sight worked. They invented approaches that took full advantage of what the equipment could accomplish. Equally vital, they illustrated that people could work successfully alongside automated systems without becoming slaves to technology or dismissing it as pointless. This reasonable middle ground regarding human-machine partnership holds importance today as automation expands across countless sectors. The Mark 18 period provides historical instruction on making such collaborations flourish and what ingredients matter most. The Mark 18 merits recognition not because it represented a dramatic breakthrough or single-handedly altered Pacific combat outcomes. It earns remembrance because it exemplifies the less flashy yet ultimately more substantial work of addressing actual difficulties effectively. When the world celebrates major innovations and transformative technologies, the Mark 18 serves as a counterweight, demonstrating that systematic, methodical improvements executed across vast numbers frequently matter more than revolutionary leaps that can't be manufactured or deployed at meaningful scale. Success followed because the device stayed practical, proved trustworthy, and worked adequately well. These characteristics, whatever they lack in romance, identify technology that genuinely changes things. At its core, the Mark 18 narrative belongs to problem solvers. Designers imagined it, factory workers assembled it, supply personnel got it where it needed to go, technicians maintained it, aviators employed it skillfully, and military leadership placed it effectively in operations. Everyone played vital roles. Removing any single contribution would have derailed everything. This cooperative foundation of technical achievement warrants recognition. Individual talent matters tremendously, but coordinated labor spanning numerous workers and institutions matters even more. The Mark 18 emerged from countless individuals performing their responsibilities competently and with dedication. That organized effort, beyond any single person's brilliance, shaped the final result. When evaluating the Mark 18's genuine impact, we must distinguish between what records explicitly confirm and what remains speculative. Documentation confirms substantial manufacturing runs, widespread installation across squadrons during 1944 and 1945, and favorable assessments from operational pilots. Mission summaries show improved shooting accuracy and quicker fights among units with mechanical rotor sights. Pilot accounts consistently highlight the Mark 18 as dramatically superior to reflector equipment for hitting moving targets. What stays difficult to pinpoint precisely from available unclassified records is exactly how much of the 11-to-1 kill advantage came specifically from the site versus other influences like better trained aviators, stronger tactics, or decreasing Japanese fighter quality. The overall 11-to-1 performance figure spans the complete war period, incorporating both equipment types. What remains obvious is that the Mark 18 signified genuine progress in aiming technology, delivering tangible benefits to operators. It showcased American manufacturing strength, engineering innovation, and methodical problem-solving. During the period when aerial combat shifted from individual brilliance toward machine-based systems, the Mark 18 represented a meaningful milestone on the way to the computerized weapon platforms characterizing modern aviation. This success rested on solid mechanics that performed dependably in battle, sufficient production quantities to outfit numerous aircraft, and pilots who could operate it competently following reasonable training. Such practical matters outweighed abstract elegance or sophisticated engineering. The Mark 18 addressed one particular obstacle: striking fast-moving targets amid intense combat. It handled that obstacle well enough to stay in use through Korean campaigns, confirming its value through extended operational experience. For those Corsair aviators carrying the Mark 18 in 1945, the sight represented simply an effective instrument, making a challenging assignment somewhat more manageable. It didn't remove peril or assure returning home, though it did enhance survival prospects in an arena where advantages mattered and fortune remained uncertain. Throughout military technology history, the Mark 18 occupies space as a transitional device. It connected the world of pure pilot instinct in air gunnery with the approaching era of radar-directed missiles. It confirmed that machines could compute faster and more accurately than human thought, a realization that would reshape flight warfare and spread far beyond combat applications. The generation who witnessed this shift grasped they were experiencing a technological upheaval that would fundamentally remake how people fought in the air. The Mark 18 symbolized both an apex and ending point for mechanical aiming systems, alongside a starting point for the electronic equipment destined to follow. Its continuing presence emerges in the fire control computers aboard contemporary fighters, sophisticated descendants of those whirling gyroscopes that originally demonstrated mechanical aiming was possible. This is the account of necessity driving technology forward, of practical knowledge meeting conflict head-on, of ideas becoming reality. It chronicles how American productive capacity and thoughtful engineering revolutionized Pacific aerial warfare, one spinning rotor mechanism at a time.